Supplemental math videos from Circle Christian School. Exponential functions. It's talking about growth and it's talking about decay. What do you do when things in nature grow by leaps and bounds? Like rabbits, you use exponents. In this case, the x is in the exponent. That's where the variable is going to be. Exponential functions. The parent function is f of x, where the base is a, but the x hangs around in the power. Now we obviously could not have a y equals 1 to a power because that would just be a straight line since it would always equal 1. So we have to start off with a base exponential, which is going to be 2 to the power of x. Using some of our rules of exponents, we can use our exponential functions, just remembering that the product rule is same base times same base, we add the powers. Same base over the same base, we subtract the powers. A base powered up from a power, we multiply the powers. And if we have a negative power, we just slide it down under the fraction bar. Okay, to evaluate an exponential function means that we're going to put the f of 5 here in the equation and evaluate. So for the first one, we would have 2 to the 5th power, which would equal 32. And for the second one, we would have 2 to the negative 1 power, which means we'd have to slide it down over the fraction bar. Same thing when we have something kind of weird and wacky, that we would put a 0 in up here. So for the first one, we would get 1.04 to the power of 0, which we know just equals 1. And likewise, if we had the base of 1.04, 2 times the square root of 2, just putting it in at x. I'm sorry, that should be the square root of 2 inside there. Beep. That, using our handy dandy little calculator, we would put in 1.04 power key parentheses, make sure you got a parentheses, 2 square root 2 parentheses, so that it would equal 1.117. Okay, likewise, when we go to graph these, if we graph our base one of 2 to the power of x, you can make yourself a little table here and see that when x is 0, y is 1. So that's where it's going through the y-axis. Likewise, when we've got 4 to a power, notice how it starts to get much skinnier. So if we have a fraction out in front of the power of x, it's going to be rather wide. And if we have the higher the number, whole number, it's just going to get skinnier and skinnier, but still go through the y-axis here at 0 and 1. See if you can't try to figure out why. There is a very good reason why. Likewise, basically, since this is a positive x right up here, and this is a negative x down here, this one has that positive motion going on, while this one has that negative motion going on. And there is a place that it kind of bottoms out at, that it never quite gets to where y is 0. And you can try your calculator with a couple different values just to see what your function looks like also. So basically what we have here is a HK situation happening. The h is going to be with the x, which is up in the power here, and the k is being added to the base with the exponent. Now the h up in the power just means that the exponential function is going to move either to the left or to the right, depending on whether it's positive or negative. Same thing here. Because it's sitting inside the parentheses, it's going to be always an opposite sign, where the K tells you if that exponential function is going to go up or down. So likewise, as long as you know what the shape is and you know what the H and the K is, you can pretty much graph where these guys are going to be at. So for instance, if I had 3 to the power of x minus 2 plus a 1, my H here would be a positive 2 and my K a positive 1. So that's kind of the vertex, that's kind of the basic part here. And knowing that this is a exponential function, that I'm just going to pretty much go through this and then start to do a rise at the same time here. A neat little base is a base that we call E, the letter E with a power. So we have a base of E and a power. We call this the natural base. This is the ones that happen with the little bunny rabbits and deer and animals in nature and radioactive decay and money when it becomes exponentially or continuously compounded. And E to the first power equals the magical number. It's a lot like pi, except for this one's going to be 2.718. Now, since E is this variable with a value, we can treat it like a variable using our exponent rules. So if we had E to the third power times E to the 1/2 power, then what we would do is use our exponent add our powers rule. And that would give us E 3.5, which just looks weird. So we would change it into the improper fraction. And if we have E's over each other, for instance, we have E to the 4th over E to the 9th, we would do the same thing. There's 4 of them here, which means we could take 4 out of the 9. It would give us 5, and we would have 1 over E to the 5th power. Or, just in this case only, since E has a value, it can actually be to a negative power, so this could be to the -5th. This is sometimes legal, only with E's. The natural base E gets used a lot in exponential growth and decay. A particular radioactive element has a half-life of 25 years. So for an initial mass of 10 grams, the mass in grams that remains after so many years, T, is given by the equation y equals 10 to the base times the base 1/2 to the power of T over 25, where T obviously isn't going to equal 0. How much of the initial mass remains after 120 years? In other words, radioactive decay is a spontaneous breakdown of atomic nucleus, resulting in the release of energy and matter from a nucleus. Remember that a radioisotope has an unstable nuclei that does not have enough binding power to hold the nucleus together. Okay, now, so we're just going to put everything back into the equation here. So when T equals 120 years, then Y is going to equal 10 times 1/2, 120 over 25. So if you do this in your calculator, you have to be very careful, especially if you do some of this by hand, to make sure that what you do is you power up the base, and the base here is 1/2 before you multiply it to the 10. Make sure you follow the order of operations. Another way to look at it is as to what is happening from year to year is actually to graph it. You can graph it up in your y equals part of your graphing calculator. Take a look at the numbers and see what they're doing. Another way we use E is with exponential money and compounding interest. There are 3 basic formulas that happen with interest, but basically you have A, which is the amount, principal, which is the money you walk in the bank with and want to invest, R equals the percent rate, N is the number of times it's being compounded, and T generally will always equal the years. So to start it off, if we were to walk in with so much money, the amount at the end of the year would be the money times the rate, the interest. So you take what you started with, add the interest, that's your amount. So after 0 years, the amount would just equal P. After 1 year, it would be the P1 plus the rate, and so forth and so on as we go down through the years here. So our base formula for any time that we're doing interest and what the amount would be, it would is the amount equals P times 1 plus the rate to the power of T. Now this actually did end up being an SAT question, remembering that when you were compounding rate, that it's always just the rate times 1 times the number of years. Plus the 1 times the principal in the years. Anyway, the formula right there. So if we have monthly compounds, say maybe we're compounding the money every month, which would be 12 months, or maybe we're doing it quarterly, which would be 1/3 of a year, or no, quarterly. Yes, quarterly would be 1/3 of the year. That the N would have to reflect so much of a year. And then if we have continuous compounds, which are the coolest ones always, which means it's just always compounding itself without any timely rate here, we use the PERT formula. The principal times that natural base E to the power of the rate times how many times it's many years that this is happening. I want you to check out example 8 for good examples, because they best show what's pretty much happening to the money, and they're pretty self-explanatory. All right, give yourself a try on the homework here. Remember, the more you do now, the less you have to do later. All right, have a good weekend.